Hello, and welcome to another edition of OpenNMS 101, the training course to get you up to speed on the OpenNMS network management platform. This lesson, I'm almost going to call it OpenNMS Lite because we're going to do very, very little with OpenNMS, and instead we're going to either review or introduce you to SNMP, the Simple Network Management Protocol. It's not the Simple Network Mail Protocol, as some websites have reported in the past. Instead, it is the protocol for managing networks. Now, in OpenNMS, SNMP it's a service and it's more. I mean, we can monitor is SNMP up or down, but that's not very, very useful. What we really use SNMP for is to gather performance data and information about the things on the network that we're monitoring. And we're going to spend, the piece of code we're actually going to spend a lot of time with in this lesson is the net-snmp agent. I am an unabashed fanboy of net-snmp. It's a very, very powerful agent, and we can utilize it to get a lot of information into OpenNMS, and we will in future chapters. Okay, the first thing you need to get your brain around when we're talking about SNMP is what is it? There's a lot of things that make up SNMP. This actually, SNMP was ratified by the Internet Engineering Task Force, the IETF, in April of 1989. For those of you who are familiar, the way the IETF works is you submit a request for comment. It goes back and forth, and finally, if it gets ratified, it becomes a standard. And they're known as RFCs. And RFC 1052 was ratified in 1989, which established this framework for managing the internet. And it consisted of many other parts. One of those was how are we going to structure this information? What type of information can we share? And how do we transmit this information from a device or an agent to a manager? And those are covered in the Network Management Protocol, SNMP, and we're going to talk about Management Information Bases, or MIBs. Now, it used to be very, very easy to find MIB information until the movie Men in Black came out. Now, when you type in MIB into any search engine, chances are you're going to get a reference to that movie and not the Management Information Base. The Management Information Base is just a data structure. I like to think of it as a code book. So basically, if you're an SNMP agent, you have a code book that describes how your information is laid out. And as a manager, I can ask for a specific piece of information, and if you support that MIB, you can return that information back. And it's actually written in a language called Abstract Syntax Notation, ASN.1. You don't really need to know this, but in the interest of no magic, we're going to spend some time working on it. I have one quick example, just for extra credit. Okay, what type of data can the Network Management Protocol share? Well, there's integers, numbers, 1, 2, 3, 4, 5, etc. You can do a string, like what type of device I am. The two main data objects we look at, especially for performance data, are counters and gauges. And a counter is a number that constantly increases. And the usefulness of a counter is it's very, very useful to measure rates. Some SNMP agents might implement a, 5-minute load average value. And so you're set at looking at a 5-minute load average. What if you want a 10-minute or a 15-minute load average? With a counter, you can choose your rate. So the way I think about it is this. Let's say, so I grew up in a small town in North Carolina, and we didn't have sports teams. We didn't have a major league football team or baseball team or anything like that. And so for fun, we would often go to baseball games hosted by the Veterans of Foreign Wars, VFW. And the VFW, there was Post 45 was in North Carolina. We go to watch Post 45 baseball games. And they were free, and when you walked to the baseball field, you'd walk by, and there was a guy at the entrance who had, we called it a clicker. It was a little device, and every time someone walked by, he would press a button. And on it was a 3-digit counter. So when no one was there, he'd reset it to 0. The first person that comes by, he'd hit click. Second person comes by, he'd hit click, and it would increment the counter. So if I was interested in how many people would come through, I might say, "Hey Zeke, what's your counter read?" And he'll go 31. And then 5 minutes later, I could say, hey, Zeke, what's your counter read? And he might say, I don't know, 56. And then I know I could take 56 minus 31, and I could say in the time between the times I'd ask Zeke what the counter was, 25 people would come by. So if that was every 5 minutes, I would know that 25 people came by in 5 minutes, or an average of 5 every minute. If I need to know faster, I can just annoy him more. Hey, Zeke, what's it read? Hey, Zeke, what does it read? Or I can sit back and wait and just get a less granular data. That's a counter. Now, a gauge is like a temperature gauge or a gas gauge. You read the instantaneous value. So if I'm looking at a thermometer, it might be 20 Celsius, it might be 20.5 Celsius, it might go down to 19 Celsius, and it might go up to 21 Celsius. So it's not a counter. You're interested in whatever the exact value is, and that's a gauge. Now, there's a special counter called time ticks. And time ticks is the number of hundredths of a second. So if I turn on something, 1 second later, its uptime in time ticks would be 100. 2 seconds later, it'd be 200, etc. So we end up getting hundredths of a second. It's just a special way of representing time within Linux and then also within SNMP. So there are a bunch of other different types of data objects, but these are the main ones. You have numbers and strings, counters and gauges, and time ticks, which, if you remember, is a special type of counter that measures time in hundredths of a second. Okay, now this data, so we have all this data that we want to monitor, and it's put in this object ID structure, this tree structure, we call it. Whenever I see this, I keep thinking about this dude. This is a picture from Wikipedia of Carl Linnaeus. Carl Linnaeus was a Swedish guy in the 1700s who was considered the father of taxonomy. And this is the study of organizing life. And he also created basically a big tree. So if you think about it, you can sit there and say, well, in this case, it was like, in the general case, it was, okay, I want to analyze life. So I might have plants and animals. And within animals, I might have those with spinal cords and those without spinal cords. And in those with spinal cords, I might have mammals and reptiles and fish. And it's basically a way of organizing a vast amount of data in this structure. This is something I got off the internet, which shows you got living organisms, and they break it into, bacteria like prokaryotic bacteria, eukaryotic bacteria, and then you've got single-cell protista, and then multicellular organisms, and from those you've got plants and animals and fungi, and then you can go and divide it all that way. And that's kind of the way they started out with the object ID. This was started out with the International Standards Organization, ISO. I think it's something else in French, but International Standards Organization fits with the abbreviation. And so everywhere on the screen here where you see a vertex, a little point, think of that as a dot. So the root of this tree is a dot. ISO is 1, so dot 1. Now, ISO has a bunch of tree structures underneath it. The one we're interested in is organizations. So it'd be dot 1, dot 3. And now the organization responsible for the Advanced Research Projects Administration, or ARPA, which founded ARPANET, was the United States Department of Defense. And its organizational number is 6. So dot 1, dot 3, dot 6, dot 1 is the first structure of this tree of organization we're going to look at. And almost every object we're interested in is going to start off dot 1, dot 3, dot 6, dot 1. Does that make sense? So again, think about it. We're trying to organize all of information into some sort of structure, and we're going to limit or preface the stuff we're interested in for SNMP to be the internet, which happens to be ISO Organization, Department of Defense, Internet, dot 1, dot 3, dot 6, dot 1. Now, underneath the internet, there are a bunch of other branches. There's a directory branch. I am not an LDAP expert. I don't know much about LDAP, but I think object IDs are used somehow in LDAP, and I think it follows under this directory tree. The two main branches of the internet tree that we're interested in is the management branch, which is dot 2, and the private branch, which is dot 4. I have worked on experimental, which is dot 3, and this is kind of where New data structures are tried out before they're actually approved and moved into the management branch. But we're not going to work too much on that here. So .1.3.6.1 is internet. .2.1 is MIB2. Now, I don't know whatever happened to MIB1. Ever since I started studying SNMP, it was always MIB2. So I don't know what happened to MIB1, but anything under here is basically something that was created by committee. It is a standard. If someone says, I support MIB2, it means they support the objects underneath the MIB2 branch. Now, I've got a handout. So, here's a piece of paper I printed out. It's a handout, two-sided piece of paper. If you want a copy, and I really think you should get one, go to www.opennms.org/training. And underneath the training, you will see capital T training. You'll see a slides directory. That's this directory here. And if you click on it, it's this SNMP reference PDF. So this SNMP reference PDF is what goes in on, that's what we need to look at now. So we're going to do the, if you want to go ahead and click on that, print out that, hit pause on the video, it'll be useful because we're going to use this to kind of talk about the MIB structure. I'll wait. No, I won't wait. Go ahead and press pause if you need to wait. We're going to get back to the slides. Okay, so here is MIB2. As you can see, it's pretty involved, and this is just a very, very, very small section of MIB2. Now, the branches under MIB2 are very generic and they get more specific. Like there is a system branch, and this contains information about what device I'm talking to. Is it a Windows server? Is it a Cisco router? Is it a Juniper switch? That is in the system tree. Now, after the system tree is the interface tree, because of course, on devices, you're going to have interfaces, network interfaces. You have to have at least one, or else it really wouldn't, you wouldn't be connected to the internet if you didn't have at least one network interface. Now notice the interfaces says nothing about protocols. There's nothing about IP or anything here. That's in another branch. So there's IP information, there's TCP information, there's UDP information, etc. And it's all in this, this MIB2 tree. Now, there are two main types of data. There are scalars. These are things that will actually end in a .0. These are things that exist only once in your MIB. So the system description, what am I looking at? It is a Windows server, or it is a Cisco router. It's not both. I can't have multiple system descriptions. It is something. Even if it was a combo device, even if it was a checkpoint firewall running on Windows, that would be the description. Now, the way you navigate to that is you would ask for an object ID that starts off .1.3.6.1. Remember, that's internet. .iso, org, Department of Defense, 6, internet. 2.1, which is the management, MIB2. So management is .2. The MIB2 is .1. The system branch is .1. System description is .1. And then the .0 tells the protocol that it only exists once. I want that instance. Things that exist once are like system description, IF number, how many interfaces I have, etc. Now there's another type of data in here, and it's represented, if you look, by anywhere this indents, and that's tabular data. So it's data that's actually represented in a table, because we may not know how many interfaces are on here. There may be 1, there may be 3,000. And so this table represents things that can actually just grow. And we index our way into a table. And so here is interface description. Again, for this object ID, notice it starts off .1.3.6.1, internet, .2.1, MIB2, .2, which is the interface branch. Again, look at your handout. .2 is IF table, .1 is IF entry, .2 is IF description, and this .3 says I want to go to the third index, index 3 in this table, and return whatever the interface description is. Now this is important, so I actually did a walk, an SNMP walk, on my Juniper switch, and this is what I came up with. So again, remember, IF table is .1.3.6.1, ISO, org, Department of Defense, internet. .2.1, MIB2. .2.2 is interfaces, IF table. .2 is IF entry. Actually, that should be .1. I'm not going to redo this slide. That should be .1. I'll redo it for my class. But IF entry is .1, so it should be .1, .3, .6, .1, .2, .1, .2, .1. And then you've got in this table, .1 is IF index, .2 is IF desker, .3 is IF type, .4 is MTU, .5 is speed. And then there's physical address, admin status, operational status, etc. There's a bunch of other stuff here. Now the index is the key that I wanted to talk to you about. So if we go back here to this slide, we're looking for this .3. Well, if we look, the .3 is this IF index, which says the IF desker would be FXP2. So if I went and looked and said, what is the description of the third interface? So if I said, what is .1, .3, .6, .1, .2, .1, .2, .2, .1, .2, .3, it would return and tell me it is FXP2. And its IF type, there's an entire IF type table. 6 just happens to be Ethernet. One of the other common ones is 24, which is loopback address. As you can see, there's a loopback address here. We've got MTUs, which is again 1514 is 1500 tends to be the MTU for Ethernet. This is actually what for IF speed for all these interfaces it returns 0. I thought about redoing the walk and coming up with something a little more interesting, but what I found out was that I wanted to point this out for the no magic piece. In this case, for these interfaces, the SNMP agent on this Juniper switch says the IF speed is 0. Now, the chances are that's not really true. I mean, with a loopback, I definitely have an interface speed. I can make queries to loopback. I can run traffic through the loopback address. But because the agent is telling me the IF speed is 0, OpenNMS, when trying to do bandwidth utilization, is going to end up running into a problem because you want to divide by IF speed to get overall utilization, and you can't divide by 0. So this is not a problem with OpenNMS. It's a problem with the fact that this particular agent, for whatever reason, I mean, I don't think there is a defined speed, so I don't think this is necessarily a bug, but I wanted to show that there's no magic here. Any management platform, including OpenNMS, is limited to the information it gets back from SNMP. And if that information happens to be wrong or not what you expect, you can't blame the management platform. You can either change it or you can deal with it in other ways. But again, this is a table. And so the key is this entry to the table is going to be some kind of index. And in this case, it's IF index. If I went here and actually asked, instead of for .2, I actually asked for .1, .3, I would get 3, because that's the IF index for the IF index of 3. These don't have to be in order. As you can see, this was 3, 4. There is no 5, 6, 7, 8, 9. That's just an artifact of the SRX that we use. And this can be, in some cases, it could be a string. This could be an IP address. But for most tables, there will be just a numeric integer where entry 1 is .1, entry 2 is .2, etc. So that makes sense. So the key takeaways here, I want to make sure everyone's on board with this, is scalars end in 0. And then tables end in some non-zero number. So if I go to the end of my object ID and the last value here is not a 0, I will know that it's not a scalar, that it's some sort of tabular data. So here's an ASN.1 example. This is for system description. And system description here is, it's an object. It consists of a display string of up to 255 characters. This is the size. It's read-only, meaning no one can change it. You really want the agent to report the system description, and you don't necessarily want a management station to be able to send a command to the agent to change it. So that's why it's read-only. There are some values, such as maybe a syscontact or system location, that is read-write, that if you have permissions, you can change it from the management station. Status is current. Another status could be deprecated. The time I saw this, remember, I'm an old guy, and I was working in this industry before Y2K, before the year 2000, and in many cases, years were represented by a display string of 2 digits. So it would be a size of 2 that would represent the last 2 digits of the year. So 97 would mean 1997. Well, instead of getting, you rarely go back and change these things. And so rather than make that particular object a 4-digit or 5-digit or an unlimited digit string, what it did was, a limited character string, what it did was just they deprecated the 2 character version, and they created a new object which represented the year in 4 characters. So you could still use it as long as you were aware that it was up to you to determine what those 2 characters meant. So if you saw 17, you knew it was 2017 and not 1917. And notice that this system description, you get this, description, a textual description of the entity. This value should include the full name and version identification of the system's hardware type, software operating system, and networking software. So there's a description. And then notice you got this weird equality, this : equals system 1. This just means that the system description is item 1 under the system tree. And in the MIB somewhere, it'll say there will be a definition of what system is. It'll be item 1 of MIB 2, and MIB 2 will be item 1 of management, and management will be item 2 of internet, all the way back to the root of ISO. Now I'm going to jump ahead just a little bit because I want to demonstrate, kind of drive home this kind of no magic thing. So here I'm up on my virtual machine that I've been using for OpenNMS, and I'm going to install net-snmp. So I'm going to do a yum install net-snmp and net-snmp utils. This will install the net-snmp agent and the forget that. I haven't started this in a while. This will go and install the net-snmp agent as well as some utilities that we can use. And the utility I want to use is snmp walk. And so if I type snmp walk, I'm going to do version 2c, -c is a community name of public. I'm going to go to my router, which is 172.20.1.1, and ask for the system description. And so if I go to the router, notice it's a string. Notice it goes systemdesker.0, and it's a string that says Juniper Networks SRX 240B Internet Router. It's running this particular kernel, and there's a few other informations, who built it, etc. And if you go back and look at our slide, a textual description of the entity should include the full name and version identification of the system's hardware type, software operating system, and networking software. So that is just a query that I've made, and this comes from somewhere in the Juniper system itself. Make sense? So it's an XRX 240B, tells you what version we're running, etc. Make sense? Again, no magic. Okay, now I told you back here that there were 2 branches we were going to deal with: management and private. Now, there's a lot of MIBs under the management branch under MIB 2. I mean, you've got the printer MIB, you've got the frame relay MIB, you've got the coffee maker MIB. It's an actual MIB. And if someone says, hey, I support the coffee maker MIB, then you would know what the object that is. They would be defined somewhere as a standard. Now, the question comes about, what if I'm Juniper or Cisco or Foundry or anybody, and I want to make MIBs that are very, very specific to my equipment? Now, if it's a standard, I could probably go to the IETF and sit on the panels, and I could say, hey, I think we should collect these data objects, etc., blah, blah, blah. But that can take a long time, and if I'm someone like a Cisco, I may not want to tip my hand to all my competitors about what I'm working on. So there is a way of actually getting this to work by using the private enterprise MIB. So basically what happens is .1.3.6.1 is internet, .4 is private, .1 is enterprises. The number that comes after that is assigned by the Internet Assigned Numbers Authority. So .2 is IBM, .9 is Cisco, .11 is HP, OpenNMS is 5813, and we should be able to go. Sometimes this doesn't load very well in Firefox, but we'll see. So enterprise, so that doesn't work. So IANA.org, there we go, enterprise numbers. This takes a really long time to load because it's huge. Does anyone want to guess how many enterprise numbers there are right now? as Firefox proceeds to die. There's just shy of 50,000. So yeah, this is going to be very unhappy. As you can see, it just killed my Firefox. I have no idea why that does that. It works fine under Chromium. So let me bring up Chrome here. Oh, come on. So INA.org/assignments. Enterprise numbers. So let me pull this up, and as you can see, make this a little bigger. If I go down here to the bottom, come on. Just taking its time getting big. This is a huge text file. Well, not super huge. Shouldn't be causing this much problems with routers. There we go. Let's try and make it a little smaller. Let's just get down to like 200. There we go. One more. So as you can see, if we go down here to the bottom, we're just shy of so 49,478. So we have just shy of 50,000 enterprise numbers, and you can apply. It doesn't cost anything. You can go get your own enterprise number if you want. I happen to have mine. So if you look for my name Taurus, let's go. There's 2432, so I have a fairly low number, enterprise number. Yeah, it is kind of like a pride thing. If you meet a bunch of network management geeks at conferences, they'll talk about who has the smaller enterprise number. It's not really a big deal when you consider that there's one called Black Pigs of Death, which is 2288, so it's a little lower than mine. But anyway, that's your private enterprise numbers. So we're still dead here. I'm going to need to get back to that. So we'll go ahead and kill that and come back to it. Okay. Getting back to our slides. So private enterprise numbers do a couple of things. First of all, you can load in MIBs. So Cisco tends to load in a whole bunch of MIBs. And every time they come out with a new protocol, they tend to add SNMP support for it, so you can get a lot of data around it. So you can load those MIBs, and the object IDs in those MIBs, for example, of Cisco, is going to start off .1.3.6.1, Internet, .4.1, Private Enterprise, .9 for Cisco. Another use of Private Enterprise MIBs is in something called the System Object ID. If you look here in the system tree, there's this thing called the System Object ID. And the System Object ID is it's an object ID that points to another object ID. And so if we go, let's go back to here. If we go and look, if we walk down the system tree, you'll see here is the System Object ID. Again, notice it's .0, there's only one. And it's enterprises, which is that .1.3.6.1.4.1. 2636 happens to be Juniper's number. And then 111.239. This will actually tell me, if I go and look at Juniper's MIB, because they have to define this, it'll tell me this is an XRX 240B, that it's a switch. First of all, it tells us what kind of device we're dealing with. So when we talk to an IBM device or an HP device or Cisco device or a Microsoft device, there's no reason for us to try to collect on object IDs that don't exist. I mean, there's no way that Microsoft Windows is going to support a Cisco object ID. The other thing is, if you've ever seen a pretty network map where there's icons and the icons show you different types of devices, nothing magical about it. They literally just have somewhere a map that says this object ID, this system object ID maps to this icon. It's how we do it with OpenNMS. If we're looking at something with a system object ID of .1.3.6.1.4.1.807.2.3.2.10, I know that's a Linux box. So I can put up a little picture of a server with a tux or something that tells me it's Linux. So again, the two things to take away from this is it tells us what device we're dealing with, so we can use it for data collection, and then we can also use it for graphical representation, etc. Does that make sense? I'm kind of throwing a lot at you. So we've got your standard object IDs, which are usually under the MIB2, which are satisfied in committee and their standards. You can download the documents, tell you exactly what they are. And then you've got private enterprise MIBs, which allow you to get vendor-specific information. And a lot of the stuff that's useful that comes out of OpenNMS is vendor-specific. Whew, okay, so we've talked about MIBs, okay. That's the data structure. How do we get information to and from a manager to an agent? Well, that's this side of the handout that I gave you. There are only 5 commands in S&P version 1. It's simple. Doesn't mean it's not powerful. You can do tons of stuff with these commands, but there's only 5 commands. S&P version 2 adds a few more, but S&P version 1, 5 commands, all you should ever need. The first one is a GET request. If I'm back here and I want to know, hey, Mr. Device, what's your value for .1.3.6.1.2.1.2.2.1.2.3, I'm going to make a GET request. So I make a GET request to the device. It will come back with a GET response. It'll say, hey, my value for .1.3.6.1.4.1.2.2.1.2.3 is FXP01 or whatever. Now, when I'm navigating a table, I can use a GET next request and say, hey, Mr. Agent, I got your value for .1.3.6.1.4.1.2.2.1.2 or whatever. What comes next? And I can either get the next object ID in the GET response, or I can get an error that says we're done. We're at the end of the table. And so that's kind of the GET part. So that's getting data and getting data from an agent from a management station. Now, there is another command called the SET request. The reason I kind of roll my eyes and pause a little bit when we talk about the SET request is that S&P sets for the longest time were not very secure. They were incredibly useful. Cisco used to have a variable, a value, an object ID, that would sit at 0. And if it ever changed to 1, it would reboot the device. So let's say I needed to install a new operating system or something. I could queue it up on the system and then write a script that says, hey, at 2 in the morning, do an S&P set to set this from 0 to 1, and then the system would automatically reboot. And of course, we assume you've tested it and all, and it's ready to go, so you're safe doing that. But sets allow a manager to make changes on the agent. It's not used very much, to be perfectly honest, just because the up until S&P version 3, it was the passwords that you used for all this were in plain text. And so the bad kids started rebooting things right in the middle of the day, so they pretty much turned that functionality off. Anyway, so GET request, GET response, GET next, that's all about getting data from an agent to a manager. SET request is the ability for a manager to change something on the agent. And finally, there's a trap. So the PDU type 4, which is it's ordinal, so 0 through 4. PDU type of 4 is a trap. And this is the ability of an agent to send an event asynchronously to the manager. Like, help, I'm overheating. Help, someone's trying to break into me. Help, my disk is full. Things like that. That's a trap. So, because all these gets and sets are initiated by the manager to the agent. And a trap is where an agent can actually send information back. And we'll spend a lot of time talking about S&P traps because they're very, very useful. Problems with S&P version 1. Now, I mentioned security. Security was done by community names. A community name was basically a password. And there were 2 main types, public and private. And public was a read-only password and private was a write-only password. Although usually in most implementations, if you used the private key in a read, it would work as well. So if you used a private key in a get, you would actually get that information back. You could have others. I mean, I saw one device I remember had like 4 or 5 different community names. So for normal stuff, you had a private key which could do some basic sets. But if you wanted to do the major stuff, you have a special community name. Again, pretty useless because if anyone can sniff the network that this is on and see the traffic, you can easily see the community name being used. So another way kind of around this was device-based security. A lot of agents would implement, hey, I'm only going to respond from commands from certain IP addresses. So if you tried to do an SNMP walk using public on my router, you wouldn't be able to get there because I don't allow SNMP traffic into my router from the outside world. But you can do device-based. I only bring this up because if you ever have OpenNMS installed and you change the IP address of the OpenNMS server, sometimes you may have to go out to your remote devices and allow the new IP address. Again, this doesn't help. Another problem that people complain about is that SNMP is UDP-based. There's nothing wrong with UDP. A lot of the internet is UDP. But the difference between TCP and UDP is like a phone call versus sending a letter in the mail. So if I send a letter in the mail, I don't get any verification that I just assume it gets there. So I put something in the mail, I assume it gets there. With TCP, you actually make a connection. It's like making a phone call. You dial a number, hello, hey, how are you? You got a little handshake. So the problem is if I want to send an SNMP trap and it's UDP, I'm not sure it gets there. And the other problem was it was limited to 32-bit counters. Now, 2 to the 32 minus 1 is a very, very large number, but it turns out that you can, especially in today's high-speed networks, end up having counters that basically, it's called a counter wrap. So if you remember my Zeke example, so Zeke's sitting there at post 45 baseball, and he's got his clicker, and it has 3 digits on it. So if I say, hey, Zeke, what's your counter read? And he says 996. And then I say, hey, Zeke, what's your counter read? And he says 5. I would know that there were 9 people had gone through because in the counter it had wrapped. It had gone 96, 996, 997, 998, 999, and then it had reset to 0. However, if I had thousands of people going through, I may not be able to keep up. So I might say, what's your counter read? And he says 54. And then what's your counter read? 20. What's your counter read? 417. What's your counter read? 312. And that actually does happen in networking, especially with the number of bytes that go through a circuit. I mean, we have 10 gig circuits out there. So we needed some other solution. And so SNMP version 2 came along. Now, this is an old slide. If you remember, SNMP started in 1988. It was ratified in 1999, fairly short process. SNMP version 2 was started in the early 90s. These were some of the architects of it. I've met Jeffrey Case. In fact, I took a SNMP course with Jeffrey Case. But I've met Marshall Rose, but I haven't met the other guys here, Keith McLaughlin or Steve Waldebusser. But they were the main architects of SNMP version 2, and they all wanted to do a ton of stuff, and they all had fairly strong egos, and they basically couldn't decide on anything. And so they finally said, well, what can we decide on? And so in 1996, 8 years after they originally started on SNMP version 1, came out with SNMP version 2. And it's often called SNMP version 2C, because one of the complaints they had dealt with how are we going to do security? How are we going to do this authentication? And they finally just said, screw it. We can't really deal with it right now. Let's just do community-based security like we used to do. So if you think about it, I mean, this is 1996. What was the most powerful CPU? It was like a Pentium 2. The ability to do strong encryption that we take for granted right now, it was hard back then. And quite frequently, I mean, this was at a time where all these vendors were trying to vie to be the fastest router vendor, etc. So quite frequently, if you threw enough traffic at something, it was going to actually just stop doing ACL checks, or it just stopped the firewall, or definitely SNMP is such a low priority in these systems. Nowadays, we're lucky we don't have to worry about it. So in 1999, they came out with SNMP version 3, which is basically SNMP version 2 with encryption. We'll talk about that in a second. So what did we get out of SNMP version 2? We got some new data types. The big one was counter 64. So we now got a 64-bit counter. 2 to the 32 is a large number. 2 to the 64 is an incomprehensibly huge number. It's one of those thought exercises where you have a chessboard with 64 squares and you put a grain of sand on the first square and you put 2 grains of sand on the second and 4 on the next, 8 on the next, 16 on the next, etc. There's like not enough sand in the world to cover that 64th thing. 2 to the 64 is a huge number. And the only time I ever really see counter wraps on a 64-bit counter is when the device itself is reset, because you'll be at some high number and it will drop to 0. The other really cool thing we got was a get bulk request. Now, if I'm trying to walk an interface table that has hundreds of thousands of interfaces, and trust me, we've actually done work with some Juniper gear which had 300,000 interfaces in the interface table. Now, these weren't physical interfaces, they were virtual interfaces, but they still count. And trying to actually ask for every single object ID was kind of not, the performance sucked. But with SNMP version 2, we can do a get bulk request, and we can say, hey, send me your interface table, and cram it in as few packets as possible. And so OpenNMS will use get bulk request if SNMP version 2 is configured, and it is by default. So I would definitely use it. SNMP version 3 is just SNMP version 2 with security, so you can encrypt the authentication. So instead of sending my password in plain text, I can actually send a hash, an encrypted password that can be read by the agent, and the agent can choose to respond on whether or not the password is valid. You can encrypt the payload. Some people don't care about the actual payload; they just want to make sure that the devices making the queries are valid. But you can encrypt the payload. You can do both, or you can do neither. And if you do neither, it's just SNMP version 2 with a lot of extra configuration. There's a few extra steps, which I'm not going to cover, but you can look on our wiki, etc., for setting up SNMP version 3. But you basically have to set up some strong passwords and what method you use to encrypt those. Okay, net-snmp. As I mentioned before, I am an unabashed fanboy of net-snmp. This grew out of the University of California at Davis, the UC Davis agent. I think after the guys graduated, they started their own project called net-snmp. It's usually configured, once it's installed, it's configured in a file called snmpd.conf. We have to edit it for permissions. By default, we don't get access to the whole MIB. By default, net-snmp limits you to the system tree and one other resource. Now, as I mentioned in here with MIB2, the interface table right here doesn't have anything to do with like IP addresses. That is in the IP branch, and there's this IP address table which maps a particular IP address to a particular IF index. And since I might know, hey, IF index 1 is my WAN connection, I might be very, very interested in the amount of traffic going through there. I need some way to relate the interface to the IF index. And so I have to have permission to look at that. Now, I've already installed with this yum install net-snmp and net-snmp utils. So I'm going to go back over here, and I'm going to go to Etsy, snmp directory. Notice there's a couple of files here. I'm going to edit the snmpd.conf file. Now, so this is one of those, depending on the operating your system is using, this file may be heavily documented, it may not. These commands should work regardless of whether or not you see what I see. This is on CentOS, and it's very, very well documented. And so this first, I'm just following the instructions here. First, map the community name to a security name. So this is the default community name here called public. We're not going to use it. So what I'm going to do is I'm going to add community to security name, and I'm going to call it the ONMS user. Now the source is default. That should allow queries from anywhere. Here's where you would limit what IP addresses could use it. You could actually put an IP address or a network range in here under the source, and that would limit who could use that community string and actually get a response. And this is an actual community name used by one of my customers many years ago. Why are you so nosy? So we're going to put that in. Notice case matters. So capital Y or capital U, SONOZ. I don't know why I cased all that. But I guess to make it so that the hackers can't find it. But anyway, so I'm going to create a new community name called Why Are You So Nosy, and I'm going to map it to the ONMS user. Now the next thing I have to do is I have to map the security name onto a group. So I'm just going to grab these two lines, and I'm going to call this my ONMS group. And I'm going to map it to my ONMS user that I used above. Again, case matters, so I want to make sure I get that right. Okay, so I'll make this pretty because I have OCD issues. And we'll just level all that up because I got to do it. Okay, so what this says is that we're going to create this group called the ONMS group, includes ONMS user, with this security model. So we've got version 1, version 2. If I left one of those lines out, I would not be able to use that protocol. I would not be able to use 1 or version 2C to access this device using that community name. This is also where you end up putting in your SNMP3 security model, which is called USM. Again, there's examples. Now, the third step, again, I'm just following the instructions, create a view. So we've got our system view, which says .1.3.6.1. Remember, .1.3.6.1 is internet, .2 is management, .1 is MIB2, .1 is system. That allows us to get to the system tree. And then it also includes this other object ID 25, which is the host resources MIB. So there's a branch dealing with hosts. And this happens to be the host uptime. When we talk about the system uptime, you'll see system uptime in here. That is the uptime of the agent. So if I restart the agent, it's going to restart the system uptime. The host resources uptime is the actual uptime of the device since it's been restarted. So we want to conclude that. So what we're going to do here is we're going to add a new view, call it all view included, and I'm just going to put .1. That gives me everything. ISO down, so .1. Now you can exclude branches. I've actually had to use this once. Many years ago, we hit a bug. It was actually, I think, a net-snmp bug that caused OpenNMS to have problems. It would scan a certain branch in the MIB and it would fail. So what we did is we created a workaround. We created an exclude rule for that object ID, so it would just never return to OpenNMS. OpenNMS would never experience the error, and so it would never have a problem. And then finally, we have to map the group, in this case ONMS group, to the view. And I call it all view. So notice that this says if I'm in the not config group, which is up here, the not config user, I'm only going to get the system view. But if I'm in the OpenNMS group, I got all view. And that should give me, if I use Why Are You So Nosy, it should give me that. So I'm going to jump back to the slides. There's a few other things we need to do, but I'm going to jump back to the slides. So again, map the community name of Why Are You So Nosy to the user, ONMS user. Map the security name, ONMS user, to a group name, ONMS group. Create a view called all view and map that to the group. So this will allow the OpenNMS group, the ONMS group, to actually see everything in the MIB. Now, the other thing we're going to do is we're going to look at the syslocation. So again, this is fairly highly commented. A bunch of different options. Notice we have the syslocation unknown and syscontact. I'm going to put, I don't know, system location, VM running on Butters, which is my machine, Taurus's desk, the OpenNMS group, 220 Chatham Business Drive, Pittsboro, North Carolina, 27312, USA, North America, Earth. Now, I know that sounds ridiculous, and it is. The Earth bit especially is a little ridiculous. I could put, Milky Way Galaxy Universe. But the reason why I put so much information in my system location is that OpenNMS can use this to group devices together. A lot of people do not leverage the power of having system location. They'll have this unknown or default. Put in a very, very good system location. So the reason is, if I wanted to see all of the devices in North Carolina, I could do a search where system location like NC, or where system location like USA or North America. So I could make categories and things in my GUI based solely on what's in the system location. And if there's an address in the system location, we can also use that to actually geotag it. We can actually put it on a map in the right location if you have an address in your system location file. So I strongly recommend you do this. Some agents, they limit it to like 64 characters. I don't know why. It's the devices where you have to go and configure them through a GUI. But for the most part, I try to be as specific as possible. And then I'll make the system contact me. Make sense? So the next thing, if you go down through the file, there's a bunch of checks. You can deal with some logs. You can monitor executables, which we'll talk about here. We want to do a disk check. So let me quit out of this for a second. If I do a df-h, notice I have a /root, /boot, and a /home. Yeah, those look interesting. So I'm going to go here, and I'm going to add disk, disk/boot, and disk/home. What these directives will do is say start. There's a disk table in net-snmp, and this will let me gather disk utilization. There's other things you can set up here. You can do load average checks. We're going to talk about extend, etc. And at the very bottom, so I'm going to go to the end here, and I'm going to add another one that says trap sync 127.0.0.1. That's localhost. So trap sync 127.0.0.1, all that's going to do is it's going to send traps to localhost. Now this is where you would put the IP address of your OpenNMS machine. Since this is a VM and I happen to know that OpenNMS is running on localhost, this is going to be fine. Let me jump back to the slides, make sure I didn't forget anything. So I won't, so I'm going to save that. And I'm going to do system control, restart SNMPD. So that should restart the SNMP daemon. Now let me bring back up. Okay. Let's get rid of that. So here is my OpenNMS web console. I'm going to go to my node. And so here is my localhost node. Again, this is running on this system here. What I was looking for, I guess I didn't get. So if I go to my events, you'll see I got a cold start trap. I'm going to talk about traps in the next exercise. But basically, when I restarted my net-snmp agent, I got a cold start trap because I'd added that trap sync. Now notice that it's not associated with any node because it came from 172.20.1.123, and we don't know where that is. Because if I go to my node, the only interface I happen to have on my node right now is localhost. But I can rescan. Well, no, I can't rescan yet. So by default, OpenNMS uses public as a community name. And so if we go here, I can do an snmp walk. So if I do snmp walk -version 2c -c public localhost, boom, you'll see I just get the system tree. This is all the stuff in the system branch and this system uptime that I was telling you about. Notice it's in time ticks. So we've had 371,211 hundredths of a second since I started this system, so it's been up for an hour. Now, if I redo this with my why are you so nosy, boom, I get a whole bunch of other stuff. And the big kicker is I want the IP adder table. So if I type in IP adder table, you can see here, that's where that 172.20.1.123 is located. So as you see, we have two interfaces. Index 1 is 127.0.0.1, and index 2 is 172.20.1.123. So how do I get that into OpenNMS? Well, I have to do two things. First of all, I'll go to the admin GUI here and configure SNMP community names by IP address. So I'm going to type in, I can do a range here, but I'm going to do 172, I'm going to do localhost, 127.0.0.1. Timeout, I'll put 3,000 seconds. Retries, 1. You don't want to either make your timeouts longer or your retries more. You don't really want to do both. And then on the community string, I'm going to put, why are you so nosy? Again, capital Y, capital U, capital Z. Why are you so nosy? Now save that. So that now just associates. So if I type in 127.0.0.1 and do a lookup, you'll see that it's why are you so nosy? It's right there. That gives me the community string. Now, if I go to my node, I can rescan. And what should happen, if everything went well, what should happen is we should discover SNMP data on this machine. And so, shouldn't take too long. Didn't. So you can see we have, wow, look, host name of this is localhost local domain. I haven't changed it. There's a system object ID. Remember that 8072.3210 tells me, hey, this is a Linux box. Here is my location. Again, VM, Butters, Tarsus Desk, the OpenNMS group, blah, 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 blah. That's exactly what I put in. I've got my contact name, and then there's the system description. And as you can see now, we have extra interfaces. There's the IPv6 interface for this particular box, and here's the IPv4 interface for this particular box. Cool, huh? Kind of neat. I want to see if I click View and Topology. I was hoping I'd be able to bring it. There we go. So I'm bringing up I did View and Topology, and you can see we have our localhost node. Notice that the icon has a little tux on it. That is because we mapped the name. Oh, come on, let's go back. That's because we mapped this object ID .1.3.6.1.4.1.8072.3.2.10 to a Linux box. Neat, huh? Okay, so going back to the slides. So what we did was we edited the snmpd file to allow for access to anything below .1 for the why are you so nosy community name. Restarted the daemon. We tested the access. Notice if we use public, we only get a small subsection of the MIB. If we use why are you so nosy, which includes that IP adder table, then when we rescanned, that we updated the community name in OpenNMS, and then we rescanned and we got information. Again, remember, we went in and we set the community name here. We discovered SNMP. We've got all these extra devices. Now notice there is a file in opt OpenNMS Etsy called snmpconfig.xml. So if I go back here, if I go to opt OpenNMS Etsy, let me clear that and show you guys. So we're in opt OpenNMS Etsy. If I look at the snmpconfig.xml, you'll see that we added a specific entry for 127.0.0.1 using the why are you so nosy community name. No magic. There's no magic in OpenNMS. It is magical, but it's not magic. And so that just shows what we did to the GUI. I could have edited it through here and restarted OpenNMS, but again, it's a lot easier to do through the GUI. And so that gives us that information. Now, another wonderful thing about OpenNMS is I can click on resource graphs now, and there is all of this information now coming from SNMP, including our disk space utilization. Now, it will take 5 minutes for this to come up. So you'll see that there's nans right now. But you didn't have to do anything to get this information. So basically what happened is when OpenNMS started, is it came up, it ran, it came up, it ran, it discovered this particular object ID, and then it automatically looked in its configuration and started collecting data. So if you're very new to OpenNMS, go and set your community names. If SNMP is enabled and it's public, you should be able to discover these devices, and it should start collecting interesting information out of the box. And we're going to discuss that more in detail. Anyway, so that's it for this lesson. I hope you found it useful. So again, what we did is we reviewed SNMP. Remember, the two things are MIBs, or code books, that talk about what information is available from an agent and how it's organized. SNMP is a protocol that allows you to get that information from a manager. An agent can send information asynchronously to a manager via a trap. And finally, we installed the net-snmp agent, did some basic configuration. Again, I love net-snmp. We're going to use it in a number of future lessons. Until then, I hope you folks have found this useful. Please feel free to leave feedback in the comments, and we'll see you next time.